Welcome to topic 1.3, representing motion. This is the biggest topic in this entire unit because kinematics is all about representing motion. So obviously, this is really embodying most of kinematics here in this one topic. And because there's so many ways to represent motion, this topic will be split into multiple videos so that way it's not just one long, boring video. Instead, you can kind of make it more digestible with splitting it into the different types of representing motion. But today, what we're going to focus on is motion graphs. So one of the ways we can represent motion is by actually graphing out the quantities we talked about last time. So I'm going to give you a narrative description of some motion, and then we're going to make a graph about it. So let's say you get out of your car. This is your car here. You get out of your car, which is 3 meters away from your house. So this 3 meters. And then you're going to go walk to your mailbox, which is 2 meters away from where you are, so a total of 5 meters away from your house. And you're going to walk there in 2 seconds. Then you're going to stop and check your mail for 5 seconds. And then you're going to go all the way back to your house in 6 seconds. So this is a little pictorial description of that motion. I gave you a narrative description, but how do we graph it? So over here, we have a little graph. We've got time on the x-axis and position on the y-axis. I know it looks kind of weird that we have x on the y-axis, but time will pretty much always be the independent variable if it ever shows up in any graph, because you can't change time. You can't do something to change time, but your position can change over time. So how do we graph this? So this origin point 0, 0, this point is going to represent if we were at the origin, which is a position of 0, which we're going to define to be the house when the time starts. So where are we when the time starts? We're at our car, which is 3 meters away from the house. So we're going to be about 3 meters up here. 3 meters. Then, in 2 seconds, we're going to be an additional 2 meters away from the house. So we're going to get a position of 5 meters after 2 seconds. Then we stop for 5 seconds. So at 7 seconds, we are at the same position the whole time because we're still at our mailbox. So here's our position there. We can draw a line connecting it. Then we go back to our house in 6 seconds. So house is 0. 6 seconds for a total of 13 seconds here. This is going to be where we're at. So this is our graph. We start at 3 meters at 0 seconds, take 2 seconds to get to 5 meters, spend 5 seconds paused, and then we spend 6 seconds going 5 meters back to the origin. Now, what if we wanted to represent this motion not with our position? What if we wanted to represent it with our velocity? Well, how do we get velocity from position? If you remember, the definition of average velocity over an interval is the change in x, change in position, over the change in time. So this might look familiar to you from your algebra class. Since x is on the y-axis and time is on the x-axis, this is the change in our y variable over the change in our x variable. And that's just the slope. So if we go to all of these points and we take the slope, we're going to end up getting the velocity. So let's start with this first interval here. slope is y2 minus y1 over x2 minus x1. We have our points 2, 5, and 0, 3. y2 is going to be 5 meters. y1 is going to be 3 meters. x2 is going to be 2 seconds. And x1 is going to be 0 seconds. So that's going to end up being 2 meters over 2 seconds, which is 1 meter per second. And if you notice, the units match, so this is indeed the units for velocity. Now, this interval here, it's flat. Whenever anything's flat, it has a slope of 0. So this is 0 meters per second. And that checks out because we're standing still at a mailbox. We're not moving. Then we go here to this last interval. We have final position 13, 0. Initial, we've got 7, 5. So that's 0 meters minus 5 meters over 13 seconds minus 7 seconds, which is going to be negative 5 meters over 6 seconds. This is going to be negative 0.83 meters per second. If you look, it's negative, because if we define positive to be going away from the house, we're coming back towards the house, which means that we're going in the negative direction. Now, I'm going to erase some of this here. Let's remember these values. What if we wanted to make a graph for velocity here? Then we just use these values and we put them on a similar graph. So I'm going to draw another graph here. Okay, so now we have our velocity and time graph. So it's just going to represent that this slope here is negative 0.83 because I erased that. So if we look over here, we've got a slope of 1 meter per second for the first 2 seconds. That means our velocity is going to stay constant at 1 meter per second up for the first 2 seconds. It's just going to be a straight line. Then we have a slope of 0 until 7 seconds, meaning our velocity is just going to be 0 during that time. If we look, we kind of have, this is how we connect them. It kind of drops down. And then we go here, and we have a slope of negative 0.833. So that's going to be here in the negatives, down here. Negative 0.83. I'm going to have that until 13 seconds. So that's how we can represent that motion in both a position time graph and a velocity time graph. Now I'm also going to show you, what if we wanted to work backwards from velocity to position? Well, how would we do that? So remember, we have velocity as change in x over change in time. So if we solve for change in x, then we get change in x is velocity times change in time. Now, how do we get that? So if we look at this box here, let's just use this as an example. We have time on the bottom here. The change in time is kind of like a base of this box. It's like the base of a rectangle. And then we have the length being the velocity over this interval. So if we were to multiply them together, we get the area of this box here, which is 2 seconds times 1 meter per second. Seconds cancel. And we get a displacement of 2 meters. So if we look back over here, we can find that that's true because displacement is final position minus initial position. We had a final position of 5 meters, an initial position of 3 meters. That means we have a displacement of 2 meters. So we can see that that's true. Now, what about acceleration? we can't really show acceleration in this example because there was no acceleration. And how do we know that there was no acceleration? Well, similar to how velocity is change in x over change in time, acceleration is change in velocity over change in time. If you see a little pattern here, that means acceleration is the slope of velocity on a graph. And everywhere here, it's just flat. So acceleration is 0, acceleration is 0, acceleration is 0. We're never accelerating. So now I'm just going to show you what it would look like if we were accelerating. I'm not going to use exact values because it's kind of hard to do, but what if we were accelerating? What would that look like? Before we get any further, I just want to give a little information about acceleration that I forgot to include in the last video. I realized I forgot to include the units of acceleration. Now, you should be able to figure these out on your own. However, I would be a bad teacher if I left you to figure them out on your own without actually ever telling you. So acceleration is change in velocity over change in time. We know the units for both of those. Acceleration units are meters per second per second. It's a measure of change in velocity. So it's how many meters per second you're changing in a second. This is a more intuitive representation of it, but how it's commonly represented is meters per second squared. Okay, on with the video. So if I were to just have some arbitrary graphs here, position, velocity, and acceleration, and let's just say I have some constant acceleration during this entire interval. Now, what would that mean for the velocity? If the acceleration is a constant positive number, that means the slope of the velocity has to be a constant positive number. Meaning, let's just start at 0 here. Our velocity would be constantly increasing, since linear graphs have a constant slope. Everywhere here, the change in velocity over the change in time is equal to this number a. Now, what would that mean for the position? If the velocity is constantly increasing, that means the slope of the position has to be constantly increasing. So how can we represent that? Let's just kind of do a mesh representation. So we have it's increasing, then its slope has to increase some more, then its slope has to increase. And if we look, this is going to end up being a curve. This isn't a very well drawn curve, but it would be some curve like this, where the slope starts small, then the slope increases steadily. And if we look here, if we get the area under, we can work out the other one. So if we have x, position versus time, velocity versus time, and acceleration versus time, to get here, to go one further, you use the slope. Find the slope of an interval, that gives you the value of this next function for the interval. But if we want to go backwards here, then we use the area. So I'll give you a little example now, and you can feel free to pause after I set up this example and try it yourself. But I will be explaining it, so once you're ready, unpause, and I can explain it. If you need a hint, you can unpause and have just the beginning explanation. So if I have this graph here of velocity versus time, with all these values, we start at 0, then after 1 second, we're at 2 meters per second. Then after 3 seconds, we're still at 2 meters per second. We stay constant there. Then we go down to 0 meters per second at 4 seconds. We go down to negative 2 meters per second at 5 seconds. So I want to know, what is the displacement at these places, what is the velocity at these places, and what is the acceleration over these intervals. Give you a second to pause and figure it out on your own if you want to. Okay, so let's start with the velocity. That's the easiest because we're given that. So we just know at 1 second, it's 2 meters per second. We can see that on the graph. Look up, 1 second, 2 meters per second. 3 seconds, also 2 meters per second. 4 seconds, 0. 5 seconds, we go across, -2 meters per second. Now let's do the next easiest one, the acceleration. We just need the slope over these intervals. So let's start here. We're going to have a final of 2 meters per second minus 0 meters per second. Then we have 1 second minus 0 seconds. That's going to give us 2 meters per second squared. So, first it's 2 meters per second squared, or 2 meters per second. That's the units for acceleration. Now here, this is flat, 0 meters per second squared. So then it's 0 meters per second squared. 3 to 4, it's going to be 0 meters per second minus 2 meters per second over 4 seconds minus 3 seconds. And that's going to be -2 meters per second squared. And then here, -2 meters per second minus 0 meters per second over 5 seconds minus 4 seconds. Again, -2 meters per second squared. Now displacement. Displacement is the area under. So at 1 second, it's going to be this area here. So this is a triangle. Area of a triangle is 1/2 base times height, which in this case is 1/2 2 meters per second times 1 second, which is just going to be 1 meter. Now, at 3 seconds, we're going to have this whole area here. So it's going to be this 1 meter displacement plus this rectangle here, which has, this is a square actually. It's got side length of 2 meters. So 1 meter plus this whole area here is what we're looking for, plus 2 seconds times 2 meters per second. That's going to be 1 meter plus 4 meters is going to be 5 meters. Now, we have that whole area plus this triangle here. So it's going to be 5 meters plus base times height. So the height is 2 meters per second. And the base is going to be 4 seconds minus 3 seconds, which is 1 second. And that is going to be an additional meter, so that's 6 meters. Now, at 5 seconds, we have that whole thing minus this area. Because if we look, this area is underneath the x-axis, meaning we're going to call this a negative. It's going to contribute negative direction. So this is going to be 6 meters minus the area of this triangle, which has a base of 1 second and a height of 2 meters per second. So that's going to be, again, 1 meter. So it's 6 meters minus 1 meter is 5 meters. Now I want to point something out. When is this speeding up? So an object speeds up not when it has an acceleration, not when it has a positive acceleration, not when it has a positive velocity, but when the velocity and the acceleration are the same sign. So when does that happen? So here, we look, what's the acceleration over this interval? 2 meters per second. What's the velocity here? It's positive, right? So here, it is speeding up. We're going to use that with an up arrow. This here, the acceleration doesn't have a sign, so it's not speeding up or slowing down. So here, it's flat. What about here? What's the acceleration here? Well, it's negative 2 meters per second squared. And what's the velocity here? Well, that's going to be positive. So this is not speeding up. This is, in fact, slowing down. And lastly, what about here? The acceleration is still negative 2 meters per second squared, but now the velocity is negative. So here it is speeding up. Even though the velocity is negative, it's speeding up here. So what happened here? It started, it sped up, it sped up, it sped up, and now it's moving at a constant speed, but it's still moving in the positive direction. Now, it's still moving in the positive direction, but it's slowing down, slowing down, slowing down. And then here, it stops. And then it turns around and starts moving in the other direction. And now it starts speeding up. So that's kind of a narrative description that we're supposed to be able to tell from this graph. So again, acceleration, velocity, same sign, speeding up, acceleration, velocity, different sign, slowing down. That's going to be it for this video. Hope you'll join us in the next one for still topic 1.3, but this time we're going to be going over kinematic equations.